Good morning and welcome to the Embedded Executive Podcast. My name is Rich Ness. I am with Embedded Computing Design. This week, my guest is Brad Booth. He is the CEO of NLM Photonics. How you doing, Brad?
Doing well. How you doing, Rich?
I'm doing very good. Thank you very much. The topic here is something that admittedly not that up to speed on, which is why I really want to talk to you. And it has a lot to do with the power that's used, required, whatever the word is, for data centers. That is such a hot topic these days, the amount of power that is needed for these data centers, which are popping up everywhere. It's really a hot button from policymakers on down to technologists. And the way that I understood it, and you'll have to correct me if I'm wrong, is that photonics has a way of being, I won't say lifesaver, but somewhat of a fix for the power struggle. So am I getting that right? Is photonics something we should be looking at to help solve this problem?
Well, somewhat right. The aspect with photonics is that they are increasing in use in data centers, and especially with AI data centers. And so that's drawing more power than most people are looking at. But there are certainly ways and avenues that we can use to reduce the power that those optical connections are using. And that's the focus that NLM Photonics has.
Okay, so when we say connections, what is it that we're connecting that we could potentially are we using photon? I'm asking lots of questions all at the same time. Are we using photonics today to do this stuff, and where in that data center is it being used?
Yeah, so if you look within a data center, within a rack today, those connections are traditionally copper. Everything outside of the rack is using optics or photonics. Um, but what we're seeing is a trend to more and more desire for optics inside the rack just because of the bandwidth requirement being placed on that system within the rack, and that requires the use of optics to be able to make those connections.
What sort of bandwidth are we talking about?
Um, ter terabits worth of bandwidth. I mean, we're, on a single link nowadays, the industry's working on 1.6 terabits per second, and the next generation coming is 3.2 terabits per second. Um, Historically, if you looked about 10, 15 years ago, that's how much bandwidth came out of a single networking switch. So now we're putting that
Mhm.
on a single fiber optic cable.
And as compared to what over copper?
Copper can do 100 gigabits per second pretty easily. So it depends on how many wires you want to put on it. So you can do 1.6 T in copper and you can do 3.2 T in copper. The challenge is you sacrifice reach, which means it gets harder to reach from the bottom of the rack to the top of the rack. And you start to sacrifice power because you have to re-amplify that signal to get it from one end to the other.
And like, are we talking about very specific numbers? Like you say, the bottom of the rack to the top of the rack. You're talking about literally just a number of feet, right?
2 meters, yeah.
Okay. Wow, that's really interesting. That's sort of it goes back to my college days with the transmission lines and things like
Yep,
that.
exactly.
Everything comes with a trade-off. What's the trade-off for optics?
So the trade-off has been with optics is a lot of the optics that we've been using today, either indium phosphide or silicon photonics, um, have been okay for being, for modulating the light. Indium phosphide is great for creating light, but it's only okay for modulating it. Silicon photonics is very dirt cheap, and so it's been used a lot, and it's grown in use. The challenge is as we're going faster, that we're kind of hitting the wall on its capabilities. And so that's really where the industry, and when you hit that wall, what happens is you have to put more power into that to make it work.
Hmm.
So now we put these massive digital signal processing chips on each end to make sure that we can recover the signal. That's a large portion of the power that's being used in those photonic links.
Can you quantify that? How much power are you talking about, and how does that compare to the more traditional methods?
So the previous methods we used to have were just standard equalizers at each end. That was back in the 10 and 100 gigabit days. Now we're talking about DSPs that are about 50% of the power of a transceiver. So if your transceiver is 20 watts, 10 watts is just going to that DSP engine.
Is there also a perception issue that you have to get past with people when it comes to photonics? That, yeah, I'm good with copper. It works. I know it's going to work.
That used to be the case, not so much anymore. Everybody's realizing that the movement to optics is just inevitable. Not to count copper out, copper will still be used in places where it's still efficient. And even Jensen Huang talks about this, that they will use copper where it's still capable to be used. But everything else outside of that range has to move to optics. It has no choice.
Now, what you alluded to a little while ago, which makes it a little more confusing for me, is that it isn't just optics. Within the umbrella of optics, there are lots of choices as well. It isn't just this.
No, no. So there's, optics is a super category for a number of ways to actually transmit light. And there's a number of different technologies and materials that can come into play. And it varies depending upon whether or not you're, say, going 100 meters or 200 meters across a data center versus going, subsea or transcontinental. So it's played across a multitude of um, application spaces. But the big challenge is how far do you need to go and what modulation scheme? And so there's all kinds of things that come into play. Um, for those of us that live in the photonics world, we just roll off words like nobody's business. But for a lot of people, the key to understand is that it is a very efficient way of moving information using light. Um, and that's why we've seen it become more and more ubiquitous throughout the communications industry.
What about reliability? I know with a copper wire, I could bang it around pretty good, and it's still going to work the way it's supposed to.
Yeah, well, we used to say, do not hit a fiber optic cable with a hammer. Because in most cases it's glass. There are certainly fiber optic cables that can handle a certain amount of stress and strain, but you have to be more careful with it because you are working with basically a glass fiber. That has certainly created some issues, but when installed correctly and not damaged, it's very reliable. What most people have discovered is actually reliability comes from either incorrectly cleaning the connectors, because if you get dust particles in the way, it just disperses light, or the other side is the laser gets too hot and it dies because lasers don't really like heat. They like to be kept nice and cool.
When you say cool, how cool are you talking about?
Oh, about 40 degrees C is kind of their where they kind of operate nicely. As you start going up, for every 10 degrees you go up, you start hitting an exponential curve of the likelihood of failure.
I actually just figured out what that meant because I spoke to somebody in the UK earlier today, and they said it was supposed to get up to 40 degrees C there today with this heat wave.
Yeah,
So
yeah,
I know that
yeah.
that's
So
just
it's
over 100 degrees.
yeah, it's what humans can tolerate. Lasers like too. 80 degrees we don't tolerate very well. Neither do lasers.
Very good, very good. Um, just to be sure the audience is familiar with NLM, what is it that you guys do?
Yeah, so NLM, the N and L and M stand for nonlinear materials. And what we work on is specific materials, organic materials, that can be used in modulating light. Today, we work on a silicon photonics platform we're agnostic actually to the photonics platform, but the industry that needs it the most right now is silicon photonics. And what we do is we have the ability to deposit our material into a silicon photonics modulator and basically put it on steroids. We amp up its capabilities, and in doing that, we reduce the size of the device and we reduce its power consumption.
Is this a technology that should be used for mainstream stuff, like in the home as well?
The home probably does not need it. I mean, it could be used in home applications, but the organic materials can be used everything from sensing to, displays, stuff like that. Organic materials, for example, are highly used in OLED TVs. That's what the O in OLED stands
Hmm.
for. So it's very similar in the fact that we have, as an industry, have started to introduce organic materials into either, display systems or into light transmission systems.
Very good. Well, I appreciate you taking the time to make me into an expert, Brad, because now I feel like I can actually have a conversation with somebody about this and know what I'm talking about.
There you go. No problem.
That was Brad Booth. He is the CEO of NLM Photonics, and I am Rich Nass with Embedded Computing Design.